imaging-based interaction by Yomna, Abdelrahman, Alireza, Sahami, Shirazi, Niels, Henze, and Albrecht, Schmidt.
Thank you. So, hi everyone, I'm Yomna Abdelrahman from Stuttgart University in Germany. I'm a second-year PhD student, and today I would like to present to you our work, Investigation of Material Properties for Thermal Imaging-Based Interaction, on behalf of my co-authors, Ali, Niels, and Albrecht. So, gestural interaction and sensing gestural interaction is one of the main focus of our research. And it has been targeted through different technologies, like in the Sixth Sense, they use RGB images to sense color-based interaction. And researchers went further in the spectrum to explore the infrared, and they used infrared projection to sense interaction. And recently, they even went further to reach the far infrared, which is also known as thermal imaging, to sense interaction based on the heat trace left behind. And the potentials of thermal imaging is really high, which made us further explore what we can have from thermal imaging. So in our initial research, we explored thermal reflectivity and how we can extend the interaction space. So basically, our bodies radiate thermal radiation because we are all above zero temperature. And the surfaces around us, they reflect these radiation. And if we have a camera that faces a surface, it still can capture our thermal radiation and the reflection of it. So basically, you can extend the interaction space to not only include the field of view, but rather the reflected view as well. And the good thing is, since thermal imaging works in a different spectrum, we can still project content. As you can see, it's reflective in the thermal band. However, it's not reflective in the visible light, so can still project visible content to interact with. However, what we miss is we don't have an insight of the recognition accuracy in the interaction in the reflected view. So in our work, we conducted a study where we had a thermal camera and a projector, and both were facing a surface. And we asked the user to stand behind the camera. And we had the 3 sets of different gestures: mid-air pointing, where we asked the user to point at the projected content. The other one was continuous gesture form of swipe, where we projected 2 points and the users were asked to move 1 point to another. And the third one is mid-air postures, which is pinch and pan. We asked the user to do the zoom in and zoom out gestures. And in order to validate the robustness of thermal imaging, we had 2 setups: indoors inside our lab and outdoors in the university campus. And for both setups, we used 4 different surfaces: glass, tile, MDF, and MDF is a process kind of wood where you can find in offices and kitchens. And finally, aluminum. We used these 4 surfaces as they are like the most common surfaces in our vicinity. So based on our results, the one interesting point is, as you can see, for the indoors and outdoors, more or less we have the same pretty similar results, which indicates the robustness of thermal imaging. It can be used in different environments regardless of the lighting conditions and the surroundings. And another thing is, glass showed the higher recognition accuracy of average of 95% for most of the gestures, for the mid-air pointing and posters and swipe. And the least one was the aluminum, and in between the tile and MDF as second and third best recognition accuracy. And this due to the fact that glass showed the sharper reflected image and aluminum showed the most blurry one. And this due to the fact that in previous work it was reported that thermal imaging and thermal reflectivity depends on the roughness of a surface. And the lower the roughness, the higher the mirror-like the reflection is. And it was even reported that there is a threshold beyond which we don't get a mirror reflection for our thermal radiation, which is 1.80 micros. So this was for the mid-air interaction in the extended reflected space. And in order to evaluate the on-surface interaction, we're interested on the temperature change at point of contact between the surface and our hands, which could be explained or like expressed in form of the temperature of the skin, temperature of the surface, and the penetration coefficient. So basically, from the name penetration coefficient, it depicts the amount of heat transferred and absorbed and penetrated to the surface. And of course, it relies on 3 other thermal properties, namely thermal conductivity, thermal density, and specific heat capacity. And in order to have a camera that can detect this heat trace, it should sense it. So in other words, in order to sense the on-surface interaction the temperature change caused should be as much as the camera sensitivity. So basically now we have 2 parameters, the roughness, which relates to the surface reflectivity, thermal reflectivity, and temperature change, which relates to the on-surface interaction and the heat trace left behind. And based on these 2 parameters, we computed it for different surfaces, glass, tile, aluminium, MDF, wood, acrylic, and we computed these 2 values for both indoors and outdoors environment. And based on the 2 thresholds I mentioned previously, like the threshold roughness, the roughness threshold and the temperature change threshold, we computed or we derived a material space that defines the possible interaction space. So basically you can divide the material space into 3 quadrants. The upper right quadrant, which is the on-surface interaction, the lower left quadrant, which is only mid-air interaction, and one in the middle, which basically both mid-air interaction through the reflected view and on-surface interaction. However, all our work was based on the camera we used. We used the Optrus PI-160, which is a basic thermal camera, and all the thresholds computed is based on our camera. However, it's not a limitation. It could be easily derived and ported for the new specs. So like here we have the temperature change threshold is the sensitivity. So if you have a different one, we just move the threshold right or left according to the camera specs. So to sum up, in our work, we assessed the recognition accuracy of interaction through the reflection of our thermal reflectivity. And we found out that thermal cameras are really robust. They can work indoors and outdoors, and we have the same recognition accuracy for both setups. And based on our investigation, we derived a material space for the interaction enabled through thermal imaging, whether it's mid-surface, mid-air through the reflectivity, or on surface through the heat trace left behind. And now I'd be happy to answer your questions.
So for questions, please walk up to the microphone again. In the meanwhile, I do have a question just from your experience. If you are in a normal office setting, with how many of these materials does it work well? And I mean, I know that in your office you have a lot of concrete. For example, you didn't test concrete, right? No. And so does it work like with most of the materials, or do you have like to select the proper interaction surface?
Like we have glass doors, so it works perfectly for the glass. And for the concrete, we didn't really test it, but the concrete has high roughness, pretty high roughness. So for the mid-air, it won't really work, but the on-surface, it could work according to the penetration coefficient. Yeah. Okay, thank you.
Good. Thanks a lot.